Okay, everyone, so now please join me in welcoming Eric, who is a PhD student at the FU in Amsterdam, and he will talk about ASLR. Please give him a warm round of applause.
Hello. Like the Herald said, I'm Eric, PhD student at the VU in Amsterdam, at the FUSEC group. And I'll be presenting work that we have done in the group today. The work I'm presenting, most of the work has been done by Ben and Kave and by Stefan, who showed that the attack that I'm presenting is applicable to all 22 CPU microarchitectures that he's tested. So credits to them. I try to sneak this slide in all my talks, but this time is especially apt because this talk is about finding them. So this talk is about attacking ASLR, which is short for address space layout randomization. It's an exploit mitigation technique, which, as far as deployment concerned, is one of the success stories. Since it's been introduced, it's been widely adopted, and it makes exploitation somewhat more difficult. The way ASLR makes it more difficult is that it changes the location of code and data usually every time the process is run, so that an attacker cannot rely on certain addresses to be the same all the time. So on the modern 64-bit architectures, the address space usually is 48 bits, which means there is about you can address about 256 terabytes of memory. Of course, this memory is not you cannot write everywhere or read everywhere because your computer probably doesn't have that much memory. So in reality, only a very small portion of the memory is allocated to a process. And so it's quite easy to change the location of this memory. So it makes life for the exploit writer a tiny bit more difficult, because it's very useful for to know the location of data. For example, if you want to overwrite a return address on the stack, then it's nice to know where you can jump to. And of course, if you don't know, you might jump into nowhere and then the program crashes. However, that not much is needed to thwart this mitigation. You just need to leak the location of the memory. So I really like this backronym. So you can try to reuse the bug that you can use to exploit to first leak information and then exploit, or if that's not possible, you'll have to find another bug which allows you to leak this location. Or maybe you don't have to. So this presentation is about an attack which uses a side channel from JavaScript on processes in the hardware itself to discover information about locations of data or code in memory. So The modern CPU architecture is a wondrous abstraction layer. So even if you, as a programmer, write machine code, there's lots of stuff you don't have to worry about, especially stuff to make your programs fast. Memory accesses are very slow on compared to your CPU on modern computers, and that's why there's a cache mechanism built in. So other things are also abstracted away. For example, if your program does a memory access, the data is written to the cache, but where is it written? Your program gives a virtual address gives off a virtual address to the CPU, which then the CPU needs to translate that to a physical address, which is done by a component called the memory management unit. So the memory management unit has a small cache of mappings from pages to from physical memory to from virtual memory to physical memory. But if that's not if an address is not in the cache, it has to do a page table walk. And the page table walk is what we're going to try to attack, and we'll measure the effect that page table walk will have on the L3 cache, the last and biggest cache in the CPU, to find out what's happening in the during the page table walk. So we're talking about doing a timing attack from JavaScript, and to measure whether memory gets accessed. So, which means that we need a pretty good timer to be able to do this. Luckily for us, the browser standards committees have come up with an API to just do that. So you can take a timestamp, do an operation, and then take another timestamp, and then you get a very crisp time measurement. Until someone published a paper which showed basically that you can do a last level cache attack on the on the CPU and discover some things. So the browser makers made the measurements much more granular. So every microsecond or so, you get a little bump, and then for 1 microsecond, nothing changes. But all is not lost for the attacker, because you can now you can turn the coarse-grained timer into a fine-grained timer. What you can do, for example, is wait for this bump to happen, and then quickly do an operation, and then start a counter. And then, depending on how long the operation takes, the counter, the longer the operation takes, the smaller the count is when the jump happens. So in Chrome, they chose to vary the length of the time when this happens. So, but still, you can do multiple measurements, and then you take an average, and then you can still get a good measurement. However, we can do better. So the browser makers decided to make this a bit more difficult, but where the standards when the browser standards committee taketh, they also giveth. So they decided to implement an object called the shared array buffer, which allows multiple threads, which are called web workers in JavaScript, to work on a single piece of memory. And they decided to enable this by default, which is actually after we published the attack. So I don't, yeah, they basically have given up on preventing nanosecond scale time measurements in JavaScript. So the shared array buffer can be used for other things, but I'll not talk about this today. So how can we measure time using shared memory? Well, it's quite simple. One thread is used for doing the timer measurement, and the other thread does the operation. And then, so when the thread which does the operation, the timer thread waits until the thread which does the operation is ready to do the operation, and then it sets a variable and starts the operation. Meanwhile, the counter thread, the timer thread, sees that the shared buffer has changed and will start counting. And then when the operation is done, the second thread changes the buffer again, and then the counter thread stops. So this gives a very crisp measurement. So now we have a nanosecond scale timer, and we can do side channel attacks from JavaScript. So we'll be doing a timer attack by on the last level cache, and when the CPU accesses memory, everything is on the granularity of a cache line, and which is 64 bytes. Within, for example, the level 3 cache, a certain physical address maps onto a certain cache set, and this cache set can, for example, on a 4-core desktop Intel machine, contain 16 different cache lines. And I'll talk about a modern Intel machine, but the concept translates to also to other microarchitectures. So per core there are 2048 cache sets, which are called a slice, and so on a 4-core machine you have 4 slices, and these slices are shared among all the cores, but it's just the way Intel has organized their cache. To get the cache set ID, so which cache set within the slice is used, you take the physical address and then you discard the 6 bits which are basically telling you which byte within the cache line you use, and then take the 11 bits next, and that is the cache set. So it's basically a round-robin mapping of the physical memory. The cache slice is some complicated hash function, and for this attack we don't need it, so we're lucky. The important thing to remember is that if two cache sets, cache lines, if physical memory map to the same cache set, they have the same offset. So the same physical address if you only regard the bits which are yeah, so they only regard the lowest bits, so that every one they have the same address modulo 128k kilobytes. So from which follows that they also must have the same address modulo 4 kilobyte, and which happens to be the size of a memory page, which is the base unit of memory management on almost all architectures, I guess, in use. So now we know this, we can do a cache side channel attack, and there are multiple attacks possible, and we'll probably use the most simple one called effect and time. So the code to do the effect and time attack is also quite simple. You have an effect function which uses a buffer and just accesses cache lines which map into a certain cache set, and we can just do that by accessing the cache line which at a certain offset of a page which we've just seen, and at this point all the cache lines should be filled with our data. So then we proceed to do an operation. We take a timestamp, we do an operation, and we time how long this takes. If this operation needs to do something with a physical memory, a cache set which maps into this, a cache line in physical memory which maps into this cache set, it will take longer because we'll have to do a memory access, and the memory accesses are really slow compared to the CPU or cache hits on modern computers. So this way we can see if this operation depends on the physical memory location which maps into this cache set. So how does this apply to the page table walk, which we'll attack? So page tables are a mechanism for processes to address a really large address space while only having a relatively small amount of physical memory. So it's basically a tree structure with tables at every level, which divide up the address space into equal parts. So the first level on Intel, which is called the fourth level because there are 4 levels. Well, so divides address space up into chunks of 512 gigabytes. The next level, so there could be 512 entries, but there don't have to be. Divide the address space into 1 gigabyte chunks, then into megabyte chunks, and then lastly into 4 kilobyte chunks, which is the granularity of a page. So each entry in there points to a memory page, a physical memory page. So what the page table walk process does is it takes the address and we'll look at this. We'll use this. We'll use a binary representation of this address because that's easier. Makes it easier to show the process. Where the 1 bits are black and the white bits are 0. So say there's a TLB miss, so we'll have to do the page table walk. Now there's a special register in the CPU which points to the first page table. Then the page table, the hardware looks at the the 9 most significant bits in the address and then uses that as an index pointer into the table. Then it does the same with the next level and with the next level and with the next level up until the level where we know the actual page, and then the 12 bits at the end will be used to point into this page. So this is a 4K page, but and so we can use this page to do a side channel attack. But what we but the observation is that the other the page tables themselves are also pages. So yeah, each of them are pages, and so we can also do a side channel attack on these pages. So let's take a look of what we can discover this way. So we can find out that a certain page gets a hit. Now there are 8 possible entries which would cause this hit. So we don't know that much, but so of all, but if we look at these pages, we can see that 6 bits are the same. So we now know that there is a sequence of 6 bits in this address that has this value that we discovered by doing the cache timing side channel. Now there are 4 levels of pages, and there's a final location into the page. So we get 5 cache colors. We assume we know the last level, the last location inside the page, because that's in practice pretty easy to reverse engineer. And even if you can't, there are other side channels to find this out. In fact, we use this final location to do the side channel attack on all the other locations. So, or actually, we try to try to not get in the way. So now we have found 4 cache lines which may be used for the page table walk. So we can see that there are 4 chunks of 3 bits that we know nothing about. And what we also don't know is which cache line is used for which level of page table. So that would give us about 16.6 bits of entropy left. So that's not a whole lot that we have gained. We still need to find 16 bits. However, there's kind of a trick. So we have a technique called sliding, where we allocate a large enough buffer, and then we just probe pages one after a time. So we just try the next page, try the next page, try the next page. It looks a bit like this. So for the last level cache page table, we just try the next page, the next page, the next page, and then when it switches, we know, okay, this was a cache line boundary. So for the next page, we know that the lowest bits of this entry are all 0 because it's just went over the boundary. This technique we can also do for the second level page tables. This time we add 2 megabytes, 2 megabytes, 2 megabytes, 2 megabytes. Still not that problematic to do from JavaScript. And then we get the whole second level page table entry. So how much entropy is left? So, well, we have got 2 chunks of 3 bits, and we don't know which page table which cache line belongs to which page table level. So we are left with 7 bits, and this is, so I think for this there's not a lot to do about this if we want to have good timers in JavaScript. But we can actually do more, because in practice stuff doesn't in practice stuff isn't optimal. So so actually nowadays we're starting to be able to allocate 1 gigabyte allocations in JavaScript, which is probably because you want to run a real tournament in there or something. But then for the last level, it's kind of too much. 512 gigabytes allocations, and then you might have to do that up to 8 times. So maybe not. However, actually, for example, for Firefox on Linux, if you allocate a certain type of object called an array buffer, Firefox doesn't initialize the memory, and it just asks the kernel for the memory and then just leaves it there. And what the Linux kernel does is it doesn't initialize it, and so it doesn't have to map in pages in the page table structure, so it just and it doesn't use up any memory as long as you don't touch it. And we don't have to touch it, we just have to go over and touch one page or one page at the very end. So this seems to so actually on Linux it turns out you can allocate huge chunks of virtual memory, and actually within seconds to minutes you can calculate the whole. You can basically do the sliding attack and flip the cache line on the highest level page table. In Chrome, Chrome does initialize memory, which is a bit unfortunate for us, but what it does is it divides memory up in heaps, and when the heap is full, or it decides, okay, maybe for security reasons I'll need to create a new one, it just to increase ASLR, actually it tries to allocate a huge, it tries to leave a huge gap between the previous heap and the new heap, which means we can move forward quickly in the address space. So using this method of creating new heaps, or we can recover the third level address bits, which would leave us with 3 bits of entropy left. And on Windows 1 or 0, I am not sure. But doing the attack on the 4th level would take a lot of time, and maybe the person because Chrome needs to initialize and free lots of memory, and it just takes time, and your laptop gets hot, so maybe the user will click away, and no ASLR for you, recovery for you. So this attack was implemented on a Skylake machine, but has been verified that it works on 22 machines by testing the side channel on a native C with a native C program. So yeah, so time for a demo video. So. So here we have obviously the browser. So these these bits are the raw measurements, and what you see here are signals detected by a solver, which kind of tries to find the most likely values for the attack. So looks really pretty matrix style. And then, yeah, the solvers try to get confidence on what they're measuring up to a certain point, and then they decide, okay, it's clear. And then attaching GDB to verify the address, we can see that the address is a location of memory that we know, and because of that we left a marker there. So that's so yeah. So in conclusion, it's possible to recover quite a lot of address information from JavaScript using hardware side channel alone on the memory management unit, and apparently browser vendors have given up on this and on other side channel attacks, because you can't have you can't have multi-processing with shared memory without this, and apparently that's the way, the direction we're going. So yeah, any questions?
As always, please line up at the microphones. We'll start with number 1, please.
Yes, have you looked at actual browser bugs and looked at how many are exploitable with just a single leaked pointer? I mean, usually you need at least 2. You need a code pointer and somewhere to write to actually gain control over the execution flow.
So in our attack, we also have a way to leak a code pointer. So we first leak a data pointer, and then we create lots of JavaScript pages, JavaScript code, and then we so leaking these most significant pages is really hard to do for code, but the last level, the ones the page tables which are which point to the actual pages, and I think also the levels, the level one level above is actually pretty easy to, well, easy. It's doable to leak using this technique.
Could we get mic number 4, please?
So you just criticized the browser creators for the, well, not trying to mitigate all these security issues. What would you, as an ASLR hacker, recommend the browsers to do? What are the measures they could take that they have not yet taken?
So, yeah, so there's also a discussion of whether ASLR, so one of the things that make this attack quite easy is that browser makers have tried to prevent against another problem called use after free vulnerabilities by allocating more memory in a different region every time, because if you can free memory and then allocate, if you allocate something else and then a bug in the browser will use it as if it were the old old object, for example, then you usually can do quite bad stuff. So I guess so you can think of mitigations against this technique, but they might work against the mitigations against use after free. So the question also becomes, do we, so is it still worth it? So yeah. Also because there are only 7 bits that are not inherent to the architecture. So yeah, the question is, in an environment where you can run JavaScript, is ASLR, it might help a bit. And sure, Ben and Kaveh spent lots of hours on implementing this, so an exploit writer might, it will still be extra effort if there's no easier way, but the question, I'm not sure.
Could we get a question from the internet, please?
Given that ASLR is only meant to help protect against remote attacks, how useful is your approach when an attacker cannot exercise the MMU?
So the attacker would always exercise MMU, but I guess choosing the location is harder, and and the timing is, of course, over the network way more difficult. So I don't really, So, but the thing is that ASLR is used for local attacks, and this against local attackers, and this shows that it's that are inherently inside the architecture problems with this, and that it's not that useful apparently.
Can we get mic number 1, please?
So recently I saw a vulnerability by the security researcher Loki Hart, which was for iOS. And in your presentation I saw, of course, the Apple Cortex, the Samsung Cortex A7, which is the iPhone 5's processor. What I'm wondering is, if I create an array in JavaScript containing my shellcode, am I able to, with this attack, to get the address of that specific array, or is that impossible?
So, so usually, I guess shellcode itself won't be executable in an array, but so you will get location of memory that you control completely, if that's what you.
Okay, that's actually what I meant.
Okay.
Yeah, cool.
Okay.
Is there a POC available, or is this kept closed source?
And I don't think we usually don't release the attack code. We do describe. We described it in the paper, so it should be reproducible using the paper.
Right. Thank you.
Yeah.
And we'll just stay at mic 1.
I didn't get the graphic you showed us in JavaScript. What were the colors and what were you trying to say there in the Y and X axis?
That's. Can you say stop, or?
In your video, for example, or?
Oh, yeah. So, so I'm not completely sure about the first one. Might be raw measurements. The second one are the 4, I think. Well, are the the page tables that that we try to the lookups that we try to find. Yeah. So you, yeah. Okay.
And more from mic 1, please.
Hello. I was just wondering if you guys actually tested this technique on public clouds or any multi-tenant architecture.
So this attack is within the browser. So yeah, we tested it as if it were a client, a browser client. Okay.
I mean, like I would like to continue actually, if it's okay.
We have a lot of time.
All right. So I read a couple of things about this. My question was not really specifically about the ASLR, but more like how could be like the mitigation techniques for like public cloud where each tenant has the right access to the cache line, and how is that, do you think, possible to disclose the cache line?
So yeah, there have been quite a few attacks using using this technique from also just natively, like you would do in a VPN environment, for example.
Is the guy
VPS environment. Oh, sorry.
You're on.
So there is a browser plugin from some researchers at TU Graz called JavaScript Zero, which aims to provide mitigation against side-channel attacks from JavaScript. Have you heard of it? And if so, have you tried if it provides protection against the attacks you showed?
So I think, yeah, so I haven't tried it, but what I described, I would say it would provide protection because it allows you to disable disable stuff you don't want, among which the shared array buffer. So in principle, the shared array buffer wasn't here before this year anyhow, and so I doubt lots of public code makes use of it. So I think it's easy to disable stuff you don't want. So JavaScript, they're basically adding stuff all the time. So to make it suitable for gaming and all kinds of sensors that you want, and and most code doesn't make use of it. For example, I only use JavaScript in my browser when the page doesn't load without. But yeah, so I'm all for disabling lots of stuff that we don't need, but the direction of the browser seems to go the other direction. So I guess we'll see how it will turn out in the end. So. Okay.
Do we have any more questions? No? Then please thank our speaker again.